So in this presentation, I'm going to look at workbook exercise 1B. That's the first one-page assignment. It's slightly trickier than some of the other direct proofs that you've seen, and we'll see why as we go along. It says, consider the series of numbers 1, 4, 7, 10, 13. So you start with 1, add 3, add 3, add 3, and so on. Give a direct proof that the product for any two members of this series is also a member of this series. So the first thing to do is to write that down in if P then Q form. So if A and B are members of, well, let's give this series a name. Let's call it S, a series of S. Then products. That means that we multiply them. So it means that A times B is also a member of S. Okay, so there's my P and there's my Q, and I want to prove that if P is the case, then Q is also the case. First of all though, the first tricky thing is I've got to work out what it means to be a member of S. In other words, what's the general form of all of the numbers in this series here? I've got to write down a formula that will effectively generate or make all of these numbers. How can I do that? Well, what I notice is that these numbers are all of the form, they get increased by 3, so they're all going to be of the form 3n plus 1. So if n is 0, 3n plus 1 is 1. If n is 1, 3n plus 1, that's 4. If n is 2, 3n plus 1 is 7, and so on. So 3n plus 1 is my formula, but what I have to ask myself is, what values can n have? The answer is, n here is a member of the natural numbers starting at 0. So definition, A is a member of S if and only if, which I write as IFF, if and only if A is equal to 3n plus 1, n being a member of the natural numbers starting at 0. Now what you might have done in your attempts at this is written n is a member of the integers. Now it's certainly the case that if I use the integers, I'll get all of these numbers, but I'll also get quite a few I don't want as well. So for example, minus 1 is a member of the integers, and if I plug minus 1 into that formula, then I get minus 2 out as a result. 3 times minus 1 plus 1 is minus 2, and that's not a member of my series. So you have to be very specific about what values n can have. Similarly, when we're testing to see whether or not A times B is a member of S, we know that it's got to have that form. So it's got to be a number of the form 3n plus 1, and we have to show that here n is a member of the natural numbers. So that's what we're trying to do. So we've got our definition of what it means to be a member of S. That's good, because A and B are going to be members of S, and hopefully, if our proof works out, A times B, the product, is going to be a member of S as well. So let's see if we can do it. So let A equal, well, let's call it 3x plus 1, and B equal 3y plus 1, and we know that x and y are both members of the natural numbers starting at 0. So in other words, x and y are two members of the natural numbers, quite possibly different, and that's going to be A and that's going to be B. And we know that A and B can be written in that form because we know that A and B are members of S, and they're all like that. So let's see what happens if we multiply them. So the product of A and B is going to be 3x plus 1 multiplied by 3y plus 1. So we're trying to show that that's in the required form, and the required form is in my definition here. How can we do that? Well, if you remember the x squared proof that I showed you, what we did next was we multiplied out the bracket. We can do that here too. So it's going to be 9xy plus 3x plus 3y plus 1. So that's our expression. What we're trying to do, we're trying to go 3 times a natural number plus 1. So we'll keep that plus 1 there, and we'll want to take a factor of 3 out. Luckily, it looks like the factor of 3 will come out very easily here. So we get 3 times 3xy plus 3x plus 3y plus 1. Sorry, just x and y there. That's it. So 3xy plus x plus y plus 1 with the factor of 3 removed. What we've now got to show is that this thing is a member of the natural numbers. Previously we've had to show that these things are integers, but for this definition it's got to be a member of the natural numbers. So we've got to be careful and make sure that we show that it's a member of the natural numbers, the counting numbers, not including any negative numbers. Well, x and y are both members of the natural numbers starting at 0. So therefore this thing, x times y, is either going to be 0 or it's going to be a positive number. We know that from the definitions. And if we multiply it by 3, well, we're either going to get 0 or we're going to get a positive number. Sorry, a positive whole number. So that we know that is a member of the natural numbers. It could be 0 or it could be a positive whole number, but it can't be negative. What about x? Well, x is a member of the natural numbers. We know that from up there. And y is a member of the natural numbers. So we've got 3xy, which is definitely a member of the natural numbers, and we've got x, which is a member of the natural numbers, and y, also a member of the natural numbers. Add them all together, we're going to get a member of the natural numbers. If we take 3 members of the natural numbers, then we must get a member of the natural numbers. So in other words, everything here in the bracket added together will form a member of the natural numbers. So let's give it a new name. Let's call it z. So 3 times z plus 1. And z is a member of n0. And that accords with our definition. So we are then finished.